Good morning. Hope you guys are doing well. Happy Tuesday. So our notes today, December 4th, 2018, are on the domains of the inverse trigonometric functions. We're going to start with a couple definitions. This should be an old definition, but let's remind ourselves of it. A function is a relation between two sets, an input set and an output set, in which there is exactly one output for any input. We often note a function using the f of x notation. So the function has the name f, the inputs are the values of x, and the outputs are the values of f of x. Then the inverse of a function, if we're using that same f notation, the inverse of a function f is denoted f to the negative 1, or f inverse. The inputs of f are the outputs of its inverse, and the outputs of f are the inputs of the inverse. So an inverse function is where we switch the inputs and the outputs, or we reflect x and y. We put all the x's in for y and all the y's in for x. You've probably already been using all this notation and these same definitions. Notice that this f to the negative 1 is the same as this sine to the negative 1. So if the function was sine of x, the inverse is inverse sine of x. All the outputs of the inverse sine are the inputs of sine. All the inputs of inverse sine are the outputs of sine. Sweet. Please feel free to pause the slide till everyone's ready to move on to the next slide. Visualizing this definition, that a relation between two sets in which there's exactly one output for any input. Okay, so here's some functions. Here we've got y equals x squared, or we might say f of x equals x squared if we were using that f notation. And here's the inverse. So if this is y equals x squared, now here I have x equals y squared. But notice the problem. Clearly here, for any one input, there's exactly one output. One input, one output. One input, one output. Remember that another way to think about that is the vertical line test, that for any one line I draw through an input value on the horizontal axis, I get exactly one output value on the vertical axis. The fact that there's only one place where this blue line crosses the red graph means that there's exactly one output for this given input, which is part of what makes it a function. The fact that anywhere I draw a vertical line, I get exactly one intersection between my graph and my vertical line is called the vertical line test. That I can draw a blue line wherever I feel like, and I'll get exactly one intersection. One intersection here, one intersection here, one intersection here. That's the vertical line test. It's another. So this is clearly a function. One input, one output. One input, one output. One input, one output. But this, where we switched all of the x's and made them y's, and all the y's and made them x's, is not a function. It doesn't pass the vertical line test. If I draw a vertical line right here, there are two outputs for one input. We don't actually know what the square root of 5 is precisely, but here, that one's really nice. There are two inputs, namely 4. There are two outputs for the input 4. If x equals y squared, then 4 has two outputs. It could be 2 squared, or 4 could equal negative 2 squared. This same input 4 has two outputs, 2 and negative 2. So this relation, x equals y squared, is not a function. If I wanted to construct f inverse of x, I would need to do something else. I would need to restrict it. I would only look at the square root of x, and I would change this, and instead of having the graph we just saw, the square root of x would only look at a part of that. It would be just this top half. Clearly, this black graph is a function. Let me reiterate. Y equals x squared is a function, but when we tried to invert it, flip all the x's and make them outputs, and all the y's and make them inputs, we ran into trouble. The inverse relation was not a function. However, we could restrict x squared to just the positive values, and then it's invertible. It's this top black part. Here's another function, y equals x cubed. It's way easier to invert. There's its inverse. So here's f of x equal to x cubed. Its inverse is super easy to construct. It equals cubed root of x. Here, every input has one output. It passes the vertical line test. One input, exactly one output. One input, exactly one output, anywhere on the domain. But it also happens to pass another test, the horizontal line test. Every output has exactly one input. This function, y equals x cubed, is invertible on its whole domain. Because when I construct this inverse function, it also passes the vertical line test and the horizontal line test. So this is not invertible on its domain, because even though it passes the vertical line test, it doesn't pass the horizontal line test. It fails the horizontal line test. The same output has two inputs. Over here, this passes the vertical line test and the horizontal line test, meaning that it is invertible on its domain. Invertible. Because its inverse is also a function. Now, all of this is stuff we're coming up against in the beginning of third quarter, so after we get back from winter break. But I thought I'd introduce it now because it helps us understand the inverse trig functions a little better, which is our topic right now in second quarter. Not invertible, invertible. Not invertible because this was not a function. This is invertible because this is a function. Okay. So here's a trig function. And just like with the parabola we were just looking at, when I try to invert it, I get this. Clearly, this passes the vertical line test. Any one input has exactly one output. But clearly, this fails the vertical line test. The same input has infinitely many outputs. Same thing here with tangent function. This passes the vertical line test, but not the horizontal line test. Even though this is a function, its inverse clearly is not a function. So what do we do about this? Well, just like with the parabola, we're going to restrict the domains of the trig functions to make them invertible. Look back at these graphs, are not invertible. Don't pass the horizontal line test. Let's add a new definition. And again, you might pause on this slide so that everyone can get it. An invertible function is a function in which the inverse is also a function. So a function is invertible if and only if the inverse is also a function. Okay. Clearly sine of x and tangent of x, and neither are any of the other trig functions, because they're periodic. They repeat themselves again and again and again, infinitely many times. The inverses formed are not themselves functions. But if we restrict the domains, just like we did with the parabola, then we can make the trig functions invertible. So the important and crucial piece of the notes today are, how do we restrict the domains of the trig functions to make them invertible? Well, let's look just at the sine function. So here's the original sine function. Obviously, we know it's not invertible across its whole domain. This would not pass the vertical line test. Fails vertical line test. Look at all of these inputs. Look at all of these outputs for just one input. One input has infinitely many solutions. Okay, so that's when I'm looking at the entire sine graph across its whole domain. But if I restricted it just from here up to here, I made it not a periodic function. I restricted it to just the domain negative pi over 2 to pi over 2, then this little piece of the sine graph would be invertible. And here's the inverse sine function, which is inverted. Here the domain was restricted to negative pi over 2 to pi over 2. So here the range of the inverse sine function is just from negative pi over 2 to pi over 2. So again, to recap, we took the original trig function sine of x. We noticed that it was not invertible on its whole domain, that when we flipped it over, one input would have many outputs. So we decided to cut it off. Cut it right here and cut it right here. And we're left with just this little piece of sine of x on the limited domain negative pi over 2 to pi over 2. And that allowed us to construct an inverse function, this one right here, inverse sine of x. Here, unlike this purple graph, every one input has exactly one output. So restricting the domain to negative pi over 2 to pi over 2 allowed us to construct this inverse function. And here's the crucial information for today. Sine graph was restricted to negative pi over 2 to pi over 2, inclusive. The cosine graph gets restricted to the interval 0 to pi to be made invertible. The tangent function gets restricted to negative pi over 2 to pi over 2 to be made invertible. Notice this is not inclusive because tangent is not defined at negative pi over 2 or at pi over 2. Cosecant, same as sine. Secant, same as cosine. Cotangent, same as secant, but again, notice that on the cotangent function, this is not inclusive because cotangent is not defined at 0 or pi. By looking at these domain restrictions that allow the trig functions to be made invertible, we find the rules for what we were calling the primary solution of a trig equation last week. So when we plug in an inverse sine of x value on our calculator, the answer is always going to be between negative pi over 2 and pi over 2. If we plug in inverse cosine of x on our calculator, we'll always get a positive value between 0 and pi. When we plug in inverse tangent of x on our calculator, we'll always get a number between negative pi over 2 and pi over 2. If our calculators had inverse cosecant, inverse secant, and inverse cotangent buttons, most of them don't, but if they did, like Desmos does, then inverse cosecant would always be on the interval negative pi over 2 to pi over 2. The answer to an inverse secant function would always be on the interval 0 to pi, and the answer to an inverse cotangent problem would always be on the interval 0 to pi. Again, feel free to pause on this slide so that everyone has the notes. When you're finished with the notes, you are welcome to either continue the Khan Academy from yesterday, if you were still working on it, start on the homework assignment for today, or hop on a computer and watch this video again if you think it would be helpful. Again, I miss you guys. The training's been really good. I think it's really helping me, but I'd much rather be teaching you, of course. Hopefully this was helpful. Feel free to send me emails if you have questions that you would like me to answer. Talk to you all soon.